Welcome once again. Let's continue with the point that we left in the first hour of the lecture. We have, if you remember, we have derived the structure of the disturbance observer, and it's now time to start analyzing the uncompensated disturbance in the system. So, analysis on disturbance compensation performance. By the way, I think I have to mention this detail here. I already sent an announcement here. I already sent an announcement in the Learn system that you can ask whatever question you want to ask through the mail. If I cannot answer or address your question, we will of course set a meeting time and we'll make a face-to-face meeting with any one of you. I know some of your friends are regularly checking out those lecture sets and asking me the questions they want to ask. I'm trying to address them with the best possible way I can. So don't hesitate to send a mail if you have any problem, any difficulty in understanding the details. One of the major comments that I received throughout those mails and face-to-face contacts was that your friends or you were mostly complaining about the lack of enough amount of examples or practical results being obtained from those lecture sets. That's normal, and actually it wouldn't go this way. We would have long lecture hours, but due to this coronavirus event, we're now having relatively shorter lectures. But if you look at the academic calendar, there is a compensation plan for the month May. In May, we will have compensation of uncompensated or uncompleted practical classes. There, if the epidemics is over, which is very low probability, but if the epidemics is over, we will try to see what we can as examples, as hands-on examples. If it's not over, I'll try to install the necessary software like the MATLAB or anything other that's required for our simulations and make one by one each and every simulation that we have regarding or referring to the material we have covered so far in that course. So don't be panic, and you'll have enough amount of examples later on being solved or being derived on the corresponding platforms for all of you. So let's make an analysis of the disturbance compensation. Well, with the disturbance observer we have, we can write this. Actually, it's in Laplace domain. Tau this is nothing but kn times I ref of s. That's actually function of s also. Minus m nominal s squared q of s, right? So if you look at the structure tau hat this of s, this is k nominal I ref of s minus m nominal s squared q of s being multiplied by g over s plus g. So we can, without loss of generality, we can write here that this is nothing but tau this of s times g over s plus g, right? So the remaining disturbance del tau del t this of s, which is nothing but the actual disturbance t this of s minus its estimation t hat this of s. It's equal to t this of s times 1 minus, because that's itself, minus t hat this was its multiplication by a low pass filter g over s plus g. If we expand this a little bit, del t this would be equal to the actual disturbance. I'm sorry, I have to write this s component again. Okay, that's equal to the actual disturbance times S plus G minus G. That makes S over S plus G. This is S over S plus G, which can be configured this way. It's equal to T this of S times, I can write here 1 over G. Actually, before this, I can write here S. If you take S out, it will be 1 over S plus G. And you can change it to 1 over G times G over S plus G. So, if you look at those components, let's write here, this is nothing but derivative operator, right? That is a scale, and this is simply low pass filter. So we can write here that the remaining disturbance in the system once we apply the disturbance observer is nothing but the actual disturbance, the derivative of the actual disturbance, sorry, scaled by a coefficient G, downscaled by a coefficient G, and filtered, low pass filtered. So this brings us the idea that bigger bigger value for that G of the low pass filter yields to smaller error in disturbance compensation. So as the system's behavior with the disturbance observer will then be system with disturbance observer. Simply we can call this DOB. System with disturbance observer will then be having that structure: K nominal times I ref is equal to M nominal times Q double dot plus del tau this. All right, and we can here assume that this term will tend to go to 0, or let me write it as will be 0 for G having very big value. Or let's explain this differently: for very big value of G. And with this in hand, if this goes to 0, we can assume that the nominal torque constant times IRF, the given current in the system, will be almost equal to the nominal mass Q double dot response of the system. So it brings us an opportunity, because if you look at this Q double dot, you can then tell that, so if we want response acceleration Q double dot response a system with DOB can give us this acceleration if we give input as q double dot desired, that's equal to q double dot response, which will be equal to k nominal over m nominal times I desired. Or I'm sorry, I have to actually modify this with a more elegant equation. It's better to identify I desired here, I reference. So if we give here I reference being equal to m nominal over k nominal, this is k nominal times q double dot desired. So it basically tells me this: m nominal over k nominal times q double dot desired. If I give this here instead of the reference current, because the reference current is in my hands and I can guide this to my system through the driver. So if I give I reference being equal to mn over kn times the desired acceleration, I will see that q double dot response will then be equal to q double dot desired. So this almost equal will become exactly equal if we assume that disturbance is perfectly cancelled. So a system with a disturbance observer can receive the desired acceleration being multiplied by mn over kn as the reference current and follow this desired acceleration in the response acceleration. That's why we are calling these systems as plant with acceleration control. The name acceleration control is because of this reason. With a system with a disturbance observer can follow the desired accelerations and can show at the response the desired acceleration. That's why it's called the plant with acceleration control framework. So let's move to the next slide. I would like to switch to the I'd like to switch to the structure where you have the inner control loop with an acceleration controller with a disturbance observer and the outer control loop with a task controller. Let's look at the task controller. This is nothing but the outer loop control. Okay. Well, we have the let's draw the things with blocks. We have the plant. And we have input to our plant. The plant has certain output, and from the output of the plant we can take signals This is disturbance observer structure that we have just drawn with a purple color. Okay, and the output of the disturbance observer will of course be fed back to our system. So this structure is usually referred as the plant with disturbance observer, because in the questions I have received, I even got this. What's plant with disturbance observer? It's this. Okay, this is plant with DOB, disturbance observer. Okay, and don't forget that here you have the color, here you have the signs with all positive identities. Okay, that's the plant with disturbance observer. Now, for the task controller, we have to be, okay, let's put here some reference. And I will call this the task controller. And task controller's output should be the desired acceleration. Sorry for my bad drawing. Okay. So here we have the long output and here the response. Okay. So the task controller should be designed in such a way that it gives us the desired acceleration so we can run it in our system. So this is called the reference. I will call this signal as the response. These are actually symbolic representations, generic representations. When we say reference, it may be the reference of velocity, reference of position, reference of anything other, maybe force reference, based on the desired task. So if you have a task controller, we have certain tasks to be accomplished, like force control or position control or velocity control, doesn't matter. So whatever that task is, the reference will be the corresponding reference. So it will be the reference of the desired task, and the response signal will be any signal that's taken from the system that could possibly be, for example, the velocity signal, the position signal, or the force signal in general. So that's the general block diagram. Now, if you remember at the beginning, before we moved on with the force control, and you have the lecture slides, the lecture notes with force control. Before the force control, we were deriving the task controllers, and we told that there are three main types of task controllers for position, velocity, or linear combination of position and velocity. Let's move on with those. So let's start, let me change the color. Let's start by simply velocity control. Okay, here, velocity controller. I'll write here task control examples. I'm writing examples. These are simply the generic types, but we're not limited with only velocity, position, or generalized error control. We can move to many different tasks. For example, for multi-degrees of freedom systems, we had the bilateral control, grasping control. In the following weeks, we'll learn how to generate motion control with time delay, how to generate motion control for constrained systems, functionally related systems, and so on. So there might be infinitely many tasks to be done by your controller. That's dependent on the desired scenario of the application. But for single degree of freedom, in order to start with the simplest cases, we start with velocity control. Don't forget, the steps are always the same. Define the error. So enforce Okay, let me make it enforce the error converge to zero value. In time. And finally, okay, I think I can change this with 1, 2, and 3 will be use 1 and 2 to obtain the desired accelerations. That's kind of a recipe for you to derive the controllers in an easy way. Let's change the color. I like using different colors. Okay, that might be a good option. For velocity control, 1 will be EV, velocity control, error. That's without loss of generality. Q dot reference minus Q dot response, isn't it? So that's the first step, defining the error. Now, once we have the error, we have to look at the structure of the error. This error structure already contains the velocity information, which means that in order to reach to the acceleration dimension, we need to differentiate this only once. And in order to enforce the zero value of error as time goes to infinity, we can enforce this dynamics on the system. EV dot plus, I can write here KV times EV is equal to 0. So this has solution of EV of t is equal to EV naught times e to minus KV KVT. So we have the initial error times exponentially decaying factor that moves our error to zero value. Now, if you look at the third item, you can use the first and the second equations to obtain the desired acceleration. This is basically taking the content, the value of EV, and substituting here. In 3, we get Q double dot reference minus Q double dot response plus KV times Q dot reference minus Q dot response should all be equal to 0. So don't forget that these signals are given by you. Okay, that's what you give. That is what you give. And okay, so user given. Let me point it. User given. And then there is also that signal that is measured, which leaves us with this. That term here, Q double dot response, should be sent to the other side as Q double dot desired. Go back to the derivation. See that response will be equal to desired for a system that has the disturbance observer, right? Okay, so if you do this, you're gonna get that Q double dot desired is nothing but Q double dot reference right here plus KV times Q dot reference minus Q dot response. Okay, if you give this desired acceleration to your system, then you will be able to control the system's velocity response in the desired way. Okay, that was the very first of our controllers, if you remember, velocity control. If you move to the next slide with position control, let's have a look at the position control. This is a little bit more complicated because of its structure. We're going to come back to this in a couple of seconds, but before we go there, let's look at the details. Define the error, enforce the error convergence to zero value, and use 1 and 2 and so on and so forth. So let's start. 1. Define the error. Let me change the color. How can we define the error? It's not so difficult. So error in position will then be equal to Q reference minus Q response. Right? That's the position control error. The second part is a little bit tricky here. What did we have in the second item? Enforce the error, converge to zero value in time. So this error can move to zero value if we apply EQ dot plus KQ EQ is equal to 0 with, of course, KQ bigger than 0. Did I mention this in the previous slide? I don't know. Well, here I have to express that KV is greater than 0, of course. It should be definitely positive. So, this equation would suffice for our goal, but it will not yield to the desired acceleration because taking the position, differentiating only once will give us the velocities, not the accelerations. In order to reach to velocities, in order to reach to the acceleration dimension, we have to be changing our dynamics with a second order one. So we can simply enforce this EQ double dot plus alpha times EQ dot plus beta times EQ is equal to 0. So here we have to pay attention to one detail. Select alpha and beta such that, okay, let me write here, based on the root behavior of a second order system. What do I mean? Well, if you look at this equation, it's nothing but s squared plus alpha s plus beta times e of s is, let me write here, eq of s is equal to 0, right? So we should look at the roots of this equation, because if we select alpha and beta arbitrarily, then we might end up with roots that respond with oscillatory behavior. So we can design this equation in such a way that it has double root at the same point, and this point can be taken relatively far away from the imaginary axis, so you have precisely and nicely exponentially decaying error. So it's up to the user to design that alpha and beta. We have covered this actually in the class. That's why I don't want to spend too much time on this. And the third item will be combining this and this. So simply substituting 1 on 3. What you have is this. Q double dot reference minus Q double dot response plus alpha times Q dot reference minus Q dot response plus beta times Q reference minus Q response should be equal to 0. So from this we will again extract the response acceleration and send it to the other side. Okay, let me draw it for you. Send it to here. Simply, we're gonna get this q double dot desired is equal to, don't forget, when we send it to the right hand side, we're now changing the notion and we're calling this as the desired acceleration, because anything given as the desired acceleration to an acceleration controllable plant will be followed at response. So you'll have the response acceleration being equal to the desired acceleration. We can write this as q double dot reference plus alpha times the error in velocity, you can call it this way, q dot ref minus q dot response plus beta times q ref minus q response as a whole. So that is our control structure. Let me highlight this for all of you. Okay, this is the second type of the controllers in single degree of freedom that we were covering. We have been covering in the class. That's the second task controller, and it's with pure position control. Don't forget that the previous one was with pure velocity control. And now we will move to the final step where we have generalized error control. Generalized error control. Here we're going to go over the same three steps as we had here, but the definition of error is important, and it comes after a modification. Here we simply define I'll call it E generalized, to be a linear combination of the velocity error, so this is q dot ref minus q dot response, that's the velocity error, plus some constant. Let me call this, well, I can call this, I think, gamma. I used already alpha and beta there. Gamma times q reference minus q response. Well, usually we have gamma greater than 1. That's, I mean, the meaning of this is we usually try to enforce the weight of the position error over the velocity error to be higher than or greater than 1. There are several reasons for that. First, velocity is a noisy and relatively dirty signal in comparison to position. Second is, if you have more power on position, you will be naturally controlling the velocity. But this dynamics is different than the previous one. That's why we have to be careful about that. Now, since this dynamics already includes the velocity term here, we cannot go and try to differentiate it 2 times, but we will be rather preferring, again, the first order differentiation. So we have here Eg dot plus Kg times Eg is equal to 0. Of course, we have to recall from this identity and write here that Kg is strictly positive, right? Otherwise, this equation would not yield to Eg of t is equal to Eg naught times E2 minus Kgt, right? Now, once you have this and that, the third was, as usual, you know, it's obvious. Take the error defined in the first step, substitute on the second step, and substitute on the equation in the second step, that's the dynamics, and get the desired accelerations. Let's try it. Q double dot reference minus Q double dot response. Plus, here you have gamma times that, let me write it here for you, gamma times Q dot ref minus Q dot response. Then then it comes, and then we come to the KGEG point. There we have plus KG times Q dot ref minus Q dot response plus gamma times Kg times Q ref minus Q response should all be equal to zero value. We can rearrange this equation as follows: Q double dot reference minus Q double dot response in our system plus, here we have gamma times the velocity error, Kg times the velocity error. We can simply write here as gamma plus Kg times the Q dot reference, the velocity error, simply Q dot response, plus gamma Kg times Q reference minus Q response is equal to 0. So from this equation, we're going to make the same trick, and we will try to pick this response acceleration, send it to the right hand side, and we will be left with this Q double dot. From now on, as we send it to the right hand side, we're going to call this as the desired acceleration, will be equal to Q double dot reference plus gamma plus Kg times, I'm sorry, it should be minus. No, it's plus. Yeah, there's no problem. Plus this times the error, Q dot reference minus Q dot response plus gamma Kg times Q ref minus Q response. So this is the desired acceleration to satisfy the tracking of velocity and position simultaneously. That's for the generalized acceleration control, or I'm sorry, generalized error control. Well, with this in mind, and referring back to that figure here, the task control structure, I think I'm done with the review part of disturbance observer and acceleration control structure. There is only one part that I didn't go over. That's the analysis of uncompensated disturbance. And I mean, it's actually here, that part, uncompensated disturbance. Would that create any problem? Yes, if you don't have a task controller, you cannot assume your system to precisely follow the given accelerations. It's going to follow the given accelerations, but it will slowly start to divert because this term is non-zero. We are assuming it to be close to zero, and in reality, yes, for very big value of g, let's take, for example, g is equal to 3000, you have delta of this to be very, very, very small, but very, very, very small doesn't mean that it's zero. So if this is non-zero, it will eventually move your system away from your reference. That's why you need here a task controller. And we have derived the task controller starting from the simplest case, the velocity control, then to position control, and finally the generalized error control. And I think this finalizes our discussion for this week. I wish all of you to have success in your midterm exams. I think most of them are over, but some of them are still on the way. So, we have announced this, but let me remind this here. We changed the structure due to this epidemics. We have changed the structure of the grading. Now we have 40% weight of project that's to be announced in the last week or maybe the last 2 weeks of the semester. Instead of midterm, we are now having the project. And the final exam, I'm waiting for the announcement from the University Administrative Council about the structures of the final exam, but it seems to me that probably this epidemics will not be over until the time of the final exams. So if it's not, then we'll not have the possibility to have face-to-face final exam, which means that I will again need to give a take-home final exam. Probably that will take no more than 24 hours of yours. So get prepared for this. Don't leave the things to the last minute, and make your reviews as much as possible. And as for the practical implementation, for the practice sessions, once more, let me tell this, in the month May, let's say in a couple of weeks, probably in 3 weeks, we will start the recovery of the practical side, the additional simulations, additional examples, solution of different examples, let me say. We will start and we'll go over those using several softwares, and hopefully we'll have opportunity to compensate those in detail. Thank you for watching, and stay at home, stay healthy until our next meeting. Take care, guys.